like you said, I'm Liz for Virginia. I'm a member of Group 3, and I'm the group reporter for the thermocouple time constant experiment. So going over the purpose and objective of this experiment, it was to practice safe laboratory procedures, observe and analyze the transient response of a type K thermocouple, become familiar with acquiring and analyzing data, and calculate and understand the physical meaning of a thermal time constant. So beginning with safety, we were required to wear safety glasses, long pants, and closed-toed shoes in the lab, and we weren't allowed to bring food or drink in. These are procedures that we've always practiced and we always will practice in mechanical engineering. So littlefuse.com describes a time constant as the time required for a thermocouple to change 63.2% of the total difference between its initial and final body temperature when subjected to a step function change in temperature. So it's essentially more of like a normalized version of time that it takes to change temperature. We used the lump capacitance method, which assumed there were no internal thermal gradients. And so manipulation of equation 1 that was given in the lab manual leads to equation 5, which has the time as a function of the normalized temperature and the time constant. So moving into our data, this was our cold water temperature versus time. As you can see, it spikes down really quickly at the beginning and then it takes a while to get back up to room temperature. And the same thing happened with the hot water, but just the opposite way around. It spiked high initially at the beginning and then took a while to get back down to room temperature. So this is the insertion temperature versus time. You can see that it only took about 2 to 3 seconds for it to get initially down to that like 9 degrees, and then took another up to 47 seconds to get down to our minimum that we got. And then coming back out, it took around 230 seconds to get back up to room temperature, so a lot longer, obviously. And then for the hot water, it only took about 7 seconds to get up to the 100 degrees Celsius. I guess shorter if you, I didn't realize that the thermocouple had gone under some steam. But then on the extraction, it takes about 260 to 270 seconds to get back down. So this was the normalized cold water temperatures versus time. Looking at the left is the insertion, and the right is the extraction. The blue line is the curve fit to the data, and the black points are the data points themselves. So again, normalizing the temperature is taking our data set and subtracting the ambient temperature. So for the cold water insertion, that would be 0 degrees Celsius. For the hot water insertion, that would be 100 degrees Celsius, and then 22, but for the extraction temperatures. And then this is the hot water data versus time, same thing with the curve fit and the data points. So then we did the log of normalized cold water temperatures versus time. So this straightened out the graphs a little bit, and this is where we get our time constants from. So again, it's insertion on the left and extraction on the right. And then the blue line is the curve fit, and the points are the data points. So to determine the time constant, it's the negative slope of the curve fit of the log of the normalized temperature versus time. So for the cold water data, which I just showed, the insertion time constant was 0.01079, and the extraction time constant was 0.008607. And then for the hot water, same thing as the cold water, and we got an insertion time constant of 0.3192 and an extraction time constant of 0.004121. So to discuss the results and the importance of procedures, the difference in time constant values for hot and cold water mainly has to do with the convective heat transfer coefficient, and that's the same with the difference between the water and the air in general. Another thing was possible errors in data. One way we could have mitigated this was by repeating the experiment multiple times and getting multiple data sets and then coming up with a mean value and a standard deviation value. So in terms of how to change the time constant, the size of the thermocouple and the material of the thermocouple is really what will change the time constant. So the time constant is density times volume times heat capacity over area times the convective heat transfer coefficient. So changing any of those is going to change your time constant, obviously. And then the effects of the procedures, we dried off the thermocouple when it came out of the water so that we wouldn't have any interruption between the convective flow of the air. We wouldn't have any water getting in the way. And then we were careful where we placed the thermocouple in the water, so we didn't want it to touch like the outside of the glass. We didn't want it to touch the bottom because that would have affected the data.